Right, I want to introduce this kinetic factor. Now, according to classical mechanics, kinetic energy is half the mass times velocity squared. But as this velocity goes up, this half goes up. And I'm going to show that this half is actually this quantity here. And as the velocity drops, this quantity, which is 1 over b, will just start flying up that way, and this will drop to a half. And then, according to particle physics, this, which is gamma minus 1, is actually the kinetic factor, and then they multiply it by c squared to get kinetic energy. But this one goes to 0 as the velocity drops to 0, whereas this one here drops to half. Okay, and then this triangle here is actually the one that they use in particle physics. So you got your rest mass, you got your momentum, and then you've got your relativistic energy. And so what they do is they put a circle through, and then this little bit here is the kinetic part, and this is the potential energy, which is this little bit here. So you got potential plus kinetic equals the total energy of the particle. Okay, but here it is on the relativistic slide rule. It's just a little part of the relativistic slide rule. Okay, so let's get out of there and let's go to the actual one. Now here it is here, the actual equation. So I started looking at it. You can see it's 0.5, but let's take it up to a velocity of 0.6 c. You can see that it's going up from 0.5. Let's take it up to 0.8. You see it's gone up to 1. Let's take it up to about 99 c. See it's gone up to 6.2. Keep going, it just keeps going up. Oops. Normally they wait. Normally they just use this one here. See, it's about the same. But as the velocity drops, they start looking a bit different. And usually at about 0.1 c, around here, they just resort to using half, because see, it looks like half. This is useless, of course, to classical physics. But this one is dropped to about half. And what happens if you keep dropping it? Well, it just gets closer and closer to half, doesn't it? Yeah, but here's an interesting thing I just want to point out. Okay, I'll keep dropping it. See, dropping. That's approaching half. Drop it. Oh, wait a minute. Drop it again. It's nearly half now. Drop it again. Wait a minute. It started going up again. Now it started going up again. Oh, it's going up again. Look, it's gone up right up to 3. So what's happening here? It's like the Higgs boson or something. It's like the Mexican hat thing. What's going on? It's like and then it craps out. It's like the uncertainty principle. What's going on? Well, I thought, it might be the anomalous magnetic moment, and it's not, though. It doesn't quite work out. So I don't know what's going on there. Anyway, back to the Earth. I'll try and get more accurate with the Earth. I've changed things around a little bit. So here's the radius of the Earth, and the B value is E, and I'm going to create another little B for the satellite, give it its own little B. So what value are we looking for? And I'm just going to make this a bit more accurate. 129673087 okay, and the radius, well, that's the radius of the Earth. Whoops. And I'm just going to throw a 2 on the front there, because that's the radius where the satellite is. Okay, now let's have a look at our Earth satellites. Okay, so I've made capital M and S for the capital B one. So you can see the centripetal acceleration on the surface of the Earth, and you can see that it's quite a lot less where the satellite is. It's only 0.57. Proper acceleration slightly above centripetal acceleration. So the equivalence principle applies to a uniform field, but of course you don't get uniform fields because everything is heading down into a gravitational well, which is actually a point. So everything's slightly heading in, and so there's a slight difference, and that's why general relativity was invented, to take account of this slight difference between centripetal acceleration and proper acceleration. Okay, because as you orbit around the Earth, your direction is changing because you're trying to point towards the center of the gravitational well. Anyway, now notice that for both B values, the mass of the Earth hasn't changed, because it doesn't really matter how big or small or how squished in that radius is, that mass is. Like, that mass could actually be squished down to the size of a black hole, which would only be about the size of a marble, and the satellite will still carry on orbiting around as it does. Nothing would change. So the mass doesn't actually change. And what I wanted to do was just show here, this is actually voltage. So say you got a clock and it's got a battery in it, and then the battery starts to go flat, then the voltage drops, and the clock starts to tick a bit slow. That's actually what's happening. So that's why clocks run slow, because the voltage is dropping. Potential energy, we call it. Energy is a very confusing concept, by the way. So anyway, let's replace this half with the truly relativistic quantity according to the relativistic slide rule, and see how it compares. Well, it's basically the same, about 38 microseconds difference, but the difference is actually slightly less when you put in the true relativistic kinetic energy, because the satellite's clock is actually slowing down slightly more because of this relativistic kinetic energy. So the difference has actually dropped a bit. So you can see here the difference has actually dropped a bit, very slightly. And same with the space. You can see the difference in the space has dropped a little bit. And there's our orbital velocities. Okay, so what about an electron traveling at 0.6 C? Well, that's gone up from 0.5 to 0.694 recurring. And what do I need to change? Okay, I've got to create the mass of the electron, so I'm going to use little b to do that. So so I don't worry about capital R, doesn't matter. Little b, I'm going to create the mass of the electron. So little b can go to h, and little r can go to the radius of the first orbital in the hydrogen atom, and there you have it, 9.1 times 10 to the minus 31 kilograms. So that's the mass. Let me take that square off. That's the momentum. Let me take that out. You got the potential energy of that first orbital, and let's just drop that one to 3 and that one to 2, and you've got the charge. Okay, now let's go down to relativistic kinetic energy. Normally particle physicists work in EV, so that would be the mass of the electron over the charge times speed of light squared. So there it is. Normally it's said to be 0.511 MeV, but that's just EV, and that actually just simplifies down to this. So that's what EV is, divided by the fine structure constant squared, which is the big mystery. Does it have units? Doesn't it have units? Well, if it doesn't have units, then that's voltage, and then we get the rest mass of the electron, the rest energy. So I've multiplied it by, I've multiplied the rest mass by c squared, and then I've cancelled the c squared with the one underneath. So that's just a simplification. So that's the rest energy. Now here's where it gets confusing when I'm just talking about energy, because at this point I'd be calling that joules, but then you've got kinetic energy, which should be added to the potential energy. This is how it's normally done, and then the total energy would be potential energy plus kinetic energy, and then we would normally call that joules, although it's really force, newtons, on the relativistic slide rule as a dimensional analysis anyway. And normally that just gets simplified, so gamma times the rest energy. So that's sort of like Einstein's equation for the energy, E equals mc squared sort of thing. And then momentum, here it is, and this is the modern way of doing it, where you just take the momentum squared plus the rest mass squared, and then you take the square root of that, and of course that's just Pythagoras theorem, and that's why I can actually show it geometrically on the relativistic slide rule, because it's just a construction from Pythagoras theorem. It's a fractal actually. Is that enough? Yeah, that'll do. Thanks.